how one engineer's stupid twin-propeller design turned the Spitfire into a 470 mph monster. At 350 miles per hour, she wants to roll left so hard I nearly put her into a spin, McKinnon said, his Scottish accent thick with frustration. The torque from that bloody great engine, it's like the propeller is trying to tear the nose clean off the airframe. Above 400 miles per hour? Forget it. No pilot alive could hold her straight in a combat situation. The numbers painted a grim picture. The Griffon 65 engine generated 1,850 horsepower at sea level, nearly double that of the original Merlin engine that had powered earlier Spitfire variants. That raw power should have pushed the aircraft past 470 miles per hour, making it faster than any German fighter in the sky. Instead, the massive torque reaction, the equal and opposite force Newton had described centuries earlier, twisted the entire airframe with such violence that pilots couldn't maintain level flight at combat speeds. Whitfield ran his hand along the propeller hub, feeling the slight vibration that never fully stopped even when the engine was shut down. The engineering challenge was brutally simple in concept, devastatingly complex in execution. Every revolution of that massive four-bladed propeller generated a rotational force that tried to spin the aircraft in the opposite direction. At low speeds, pilots could compensate with rudder input and muscle, but as airspeed increased, the aerodynamic forces amplified the problem exponentially. The result was an aircraft that became progressively more dangerous to fly the faster it went, exactly the opposite of what combat demanded. The Germans have the same problem with their high-powered fighters, Whitfield said, though his tone carried no comfort. Their Focke-Wulf 190 series suffers from similar torque issues, but they've learned to work around it with pilot training and tactical limitations. McKinnon shook his head sharply. We can't work around physics, Malcolm. This isn't about pilot technique or training protocols. At the speeds we need to achieve air superiority over Western Europe, this aircraft is simply unflyable. He didn't need to finish the sentence. Everyone in that hangar understood the stakes. The Ministry of Aircraft Production had already invested millions of pounds developing the Griffon engine and redesigning the Spitfire's airframe to accommodate its increased size and weight. Production schedules called for hundreds of these aircraft to begin rolling off assembly lines within months. The Royal Navy desperately needed the naval variant, the Seafire, to match the performance of American carrier-based fighters in the Pacific theater. Failure wasn't just an engineering setback. It represented a potentially catastrophic gap in Allied air power at the most critical phase of the war. 15 miles away, in the cluttered office of Rotol Air Screws Limited, Joseph Smith sat surrounded by technical drawings, slide rules, and empty teacups. The chief designer had spent the past week analyzing flight test data from the troubled Spitfire, searching for a solution that his colleagues increasingly believed didn't exist. The conventional approaches had all failed. Increasing rudder size added weight and drag without solving the fundamental problem. Modifying the engine mount to reduce torque transmission weakened the airframe structure. Adjusting propeller blade angles helped marginally, but created new problems with efficiency and vibration. Smith stared at his calculations, seeing not what was, but what could be. At 42, he possessed an intuitive understanding of aerodynamics that bordered on genius, but his solutions often struck more conservative engineers as needlessly complex or impractical. He had designed propeller systems for Rolls-Royce that pushed the boundaries of what manufacturing technology could achieve, earning grudging respect for their performance and equally vocal criticism for their production challenges. The concept emerged from Smith's understanding of torque as a fundamental force rather than a problem to be suppressed. Instead of fighting the Griffon engine's massive rotational energy, what if they harnessed it? Two propellers, mounted on the same shaft, spinning in opposite directions. The contra-rotating propellers would cancel out each other's torque reaction while delivering unprecedented thrust efficiency. The physics were elegant, almost beautiful in their simplicity, but the engineering challenges were staggering. The system would require a complex gearbox to drive both propellers from a single engine output, adding weight and mechanical complexity to an aircraft already pushing the limits of structural design. The contra-rotating propellers would need to be precisely balanced to prevent catastrophic vibrations. The entire assembly would have to withstand the enormous stresses of combat maneuvering. Most critically, the system would have to be reliable enough for mass production and field maintenance under wartime conditions. When Smith first presented his drawings to the Rotol engineering team, the response was immediate and overwhelmingly negative. Senior engineer Robert Morrison called it a mechanical Rube Goldberg contraption that would be impossible to manufacture in quantity. Production manager Charles Henley worried about the weight penalty and maintenance requirements. Test engineer David Clark questioned whether the system could survive the stresses of carrier operations for the naval Seafire variant. "It's simply too complex, Morrison argued during a heated meeting in Smith's office. "We're talking about essentially building two complete propeller systems and somehow making them work together perfectly. The gear ratios alone will require precision manufacturing that we can barely achieve under peacetime conditions, let alone with wartime production pressures." Smith had done his calculations. The contra-rotating system would indeed be heavier than a conventional single propeller, roughly 200 pounds more, but the elimination of torque reaction would allow the aircraft to achieve its full speed potential. More importantly, the improved propeller efficiency would actually increase thrust by nearly 15%, more than compensating for the additional weight. The Spitfire Mark 21 could finally become the 470-hour MPR interceptor that the Royal Air Force desperately needed. But first, he had to convince men who thought his idea was insane. "Gentlemen," Smith said quietly, spreading his technical drawings across the conference table, "I understand your concerns. This system is complex. It is unconventional. But consider what we're facing. An aircraft that becomes a liability at the exact speeds where we need it most. We can continue pursuing incremental improvements that might gain us 10 or 15 miles per hour, or we can solve the fundamental problem." Morrison leaned back, arms crossed. "And if it fails? If this contraption tears itself apart at 400 mph, we've wasted months we don't have and resources we can't spare." "If we do nothing," Smith replied, meeting his gaze, "the Mark 21 will never see combat. The ministry will cancel production, and we'll have lost those same months anyway, along with any chance of air superiority when the invasion comes." The room fell silent. Outside, the October rain continued its relentless drumming, counting down the seconds Britain couldn't afford to lose. The war wouldn't wait for perfect solutions. But it might, just might, reward the kind of radical thinking that transformed impossible ideas into battlefield reality. Before we continue, click that subscribe button, like this video and let me know in the comments where you're watching from. It brings me great joy knowing that these war stories and lessons get to people all over the world. Your support helps us bring more thrilling war stories, and trust me, you won't want to miss them. Now, let's get back to the story. The Ministry of Aircraft Production's boardroom in London felt more like a tribunal than an engineering conference when Smith arrived on the morning of November 15, 1943. Around the mahogany table sat some of Britain's most senior aviation officials, their faces bearing the weight of a war that had already consumed 4 years and showed no signs of ending quickly. Air Marshal Sir Wilfrid Freeman presided over the meeting with the grim efficiency of a man who had watched too many promising aircraft designs fail when they were needed most. "Mr. Smith," Freeman began, his voice carrying the clipped authority of the Royal Air Force, "we've reviewed your proposal for this contra-rotating propeller system. I must say, the initial reaction from our technical staff has been skeptical." He gestured to a stack of reports that seemed to tower over Smith's modest folder of drawings. "The consensus appears to be that your design introduces unnecessary complexity at precisely the moment when we need proven, reliable solutions." Smith had expected this resistance, but the formal setting made his throat tighten with nervous energy. These men controlled the fate of British aviation, and their decision would determine whether his months of calculations and sleepless nights had any meaning beyond academic exercise. "Sir, with respect, I believe the complexity of the system is precisely what makes it effective. We're not simply adding components, we're fundamentally solving the torque problem that has made the Griffon engine unusable at combat speeds." Director of Technical Development Sir Roy Fedden leaned forward, his reputation as one of Britain's most accomplished engine designers lending weight to his skepticism. "Mr. Smith, your proposal calls for a gearbox system that would make this propeller assembly the most complex ever fitted to a fighter aircraft. We're talking about contra-rotating shafts, planetary gear reduction, and precision timing that must remain perfect under combat conditions. The maintenance requirements alone could ground entire squadrons." The numbers Smith had prepared told a different story, but he knew that raw data wouldn't be enough to overcome institutional inertia. "The gearbox complexity is manageable with proper manufacturing tolerances," Smith replied, his voice steady despite the mounting pressure. "De Havilland has already proven that complex propeller systems can be mass-produced with their variable pitch mechanisms. Our system would use a 2-stage planetary gear train, the differential rotation speeds precisely calculated to cancel torque while maximizing thrust efficiency." Group Captain Peter Thornton, representing operational requirements, shuffled through a folder of combat reports from Mediterranean and Pacific theaters. "Even if your system works mechanically, Mr. Smith, we're concerned about weight and balance. The Mark 21 is already heavier than previous Spitfire variants. Adding 200 pounds of additional propeller machinery could affect performance in ways we don't fully understand." Smith pulled out his most carefully prepared calculations. "The weight penalty is real, sir, but the performance gains more than compensate. Our estimates show a thrust increase of 15%, combined with complete elimination of torque reaction. The aircraft would not only achieve its design speed of 470 mph, but maintain controllable flight characteristics throughout the entire speed range." What Smith didn't mention was the mounting pressure from intelligence reports about German aircraft development. The Allies needed every possible advantage in air speed and maneuverability to maintain air superiority over Western Europe during the anticipated invasion. Freeman consulted his notes, clearly weighing the technical risks against operational necessities. Your proposal would require significant modifications to existing production lines. How long would it take to develop a working prototype? Assuming we authorize the project, 6 weeks for the initial gearbox design and manufacturing, sir. Another 4 weeks for propeller fabrication and balancing. We could have a test installation ready for flight trials by early February. Smith's confidence masked the enormous technical challenges involved. The contra-rotating system would require precision engineering that pushed British manufacturing capabilities to their limits. The room fell silent as the officials absorbed the timeline. 6 months had passed since the first troubled flight tests of the Griffon-powered Mark 21, and pressure from operational squadrons was mounting. Air Commodore Ralph Sorley, who had overseen fighter development throughout the Battle of Britain, finally broke the silence. "Mr. Smith, your reputation suggests that when you propose something this unconventional, it's worth serious consideration. But I must ask directly, are you absolutely certain this system will work? We cannot afford another failed modification program." Smith met Sorley's gaze directly. "Sir, I stake my career on it. The physics are sound, the engineering is achievable, and the performance gains are exactly what the Royal Air Force needs." The bold statement hung in the air like a challenge. Freeman exchanged glances with his colleagues, recognizing that Smith's confidence carried the weight of genuine technical expertise. "Very well," Freeman said finally. "We'll authorize a limited development program, 1 prototype installation, full flight testing, and complete performance evaluation. But understand, Mr. Smith, if this system fails, or if it delays Mark 21 production by even a month, the consequences will extend far beyond your career." The morning of February 23, 1944, dawned gray and bitter across the Salisbury Plain, with winds gusting to 25 knots across the experimental airfield at Boscombe Down. Inside Hangar 7, the modified Spitfire Mark 21 sat like a mechanical alien among its conventional siblings, the massive contra-rotating propeller assembly dominating its nose with an almost predatory presence. Test pilot squadron leader Jeffrey Quill approached the aircraft with the careful attention of a man who understood that he was about to risk his life on an unproven theory. His reputation for precise aircraft evaluation had earned him assignment to the most experimental programs, but nothing in his experience had prepared him for the mechanical complexity now mounted on the nose of Spitfire serial number RK958. The contra-rotating propeller system represented 6 months of intensive engineering by Smith's team at Rotol. The forward propeller rotated clockwise at 1,825 revolutions per minute, while the rear propeller spun counterclockwise at 1,475 revolutions per minute. Between them sat a gearbox weighing 193 pounds, machined to tolerances normally reserved for precision clockwork. Chief Test Engineer Michael Lithgow supervised the pre-flight inspection with nervous energy that infected everyone in the hangar. The gearbox temperatures stayed within normal ranges during ground running, he reported to Quill. "But Jeffrey, we're still seeing harmonic vibrations at 1,800 engine revolutions per minute that we can't fully explain." Smith stood quietly near the aircraft's port wing, his face betraying none of the anxiety that had kept him awake for the past week. Every calculation had been checked and rechecked, every component tested to destruction limits. Yet aircraft design remained as much art as science. At precisely 9:15, Quill strapped himself into the familiar cockpit, though the instrument panel now included additional gauges for monitoring the complex propeller system. The Rolls-Royce Griffon engine fired with its characteristic deep rumble, but the sound was immediately altered by the contra-rotating propellers into something entirely new. The Spitfire began its takeoff roll with surprising smoothness, the contra-rotating propellers eliminating the familiar left-turning tendency that every Spitfire pilot had learned to counteract. For the first time in months of testing, the Mark 21 tracked straight down the runway centerline without constant pilot correction. Liftoff occurred at 85 miles per hour exactly as predicted, but Quill immediately noticed something wrong. The aircraft felt sluggish in the climb, requiring more power than expected to maintain a reasonable rate of ascent. By the time he reached 5,000 feet, he was using nearly full throttle to maintain 2,000 feet per minute climb rate, performance that should have been easily achievable at 75% power. "Boscombe Control, this is Test 27, Quill radioed. I'm experiencing higher than expected power requirements. Requesting permission to level off at 6,000 feet for handling evaluation." At 300 miles per hour, the aircraft that had previously tried to roll uncontrollably now flew with steady precision. The elimination of torque reaction had transformed the Mark 21's handling characteristics. Quill experimented with gentle turns, steep banks, and rapid direction changes, finding that the aircraft responded with agility that seemed impossible for such a large, heavy fighter. But when he advanced the throttle toward maximum power, the aircraft's performance became genuinely alarming. At 370 mph, the entire airframe began to shake so violently that he could barely read his instruments. The contra-rotating propellers, designed to operate in perfect harmony, seemed to be creating destructive interference patterns that threatened to tear the aircraft apart. "Boscombe Control, Test 27, experiencing severe vibration above 370 mph, Quill reported, his voice tight with concentration as he reduced power. "I'm returning to base for emergency landing." Quill touched down after 43 minutes of flight testing, his face grim with the knowledge that Smith's revolutionary design had failed its first crucial test. The contra-rotating propellers worked as advertised in eliminating torque reaction, but they had introduced new problems that might prove even more dangerous than the original difficulties. As ground crews swarmed over the aircraft, checking for structural damage from the severe vibrations, Smith approached with the expression of a man watching his life's work crumble. The emergency meeting convened in Hangar 7 2 hours later, with Smith facing a circle of engineers, test pilots, and ministry officials whose expressions ranged from disappointment to barely concealed anger. Air Commodore Sorley had driven down from London immediately, and his presence transformed what should have been a technical debriefing into something resembling a court-martial. "Squadron Leader Quill," Sorley began, "please give us your complete assessment." "Sir, the contra-rotating propellers completely eliminated torque reaction during takeoff and low-speed flight," Quill reported. "Handling below 300 mph was exceptional, possibly the best I've experienced in any Spitfire variant." A murmur of surprise rippled through the assembled engineers. "However," Quill continued, his tone becoming more somber, "above 300 mph, the aircraft experienced severe vibrations that made further speed increases impossible. Additionally, climb performance was significantly degraded. Smith felt the weight of failure settling on his shoulders. He had solved the torque problem only to create vibration issues that were potentially more dangerous. "Mr. Smith," Sorley said grimly, "the question now is whether these problems can be solved within a reasonable time frame, or whether we should abandon this approach entirely." Smith refused to accept defeat. "Sir, I believe the vibration problems can be resolved through modifications to the propeller blade design and gearbox timing. The fundamental concept remains sound." Despite having risked his life that morning, Quill found himself unexpectedly supporting Smith's position. "With respect, sir, the aircraft's handling below 370 mph was remarkable. If Mr. Smith can solve the high-speed vibration issue, we could have an aircraft that combines the Griffon's power with handling characteristics that exceed any fighter currently in service." Smith seized the moment. "The vibration analysis suggests the problem lies in the relationship between propeller blade angles and rotational speeds. By adjusting the gear ratios to alter the speed differential, we can shift the harmonic frequencies away from the critical resonance points." Lithgow looked up from his calculations with cautious optimism. The modifications would require approximately 3 weeks of machine shop work. We could have the aircraft ready for second phase testing by mid-March. Sorley consulted his pocket watch, calculating timelines against competing priorities. Finally, he spoke. "Mr. Smith, you have one more opportunity. But understand, this represents the absolute limit of our patience. If the second test flight fails to demonstrate clear improvements, we will abandon the contra-rotating propeller program entirely." As the meeting dispersed, Smith remained in the hangar, staring at the silent Spitfire. The next 3 weeks would determine whether his stupid idea would revolutionize fighter aviation or become a cautionary tale about the dangers of challenging conventional wisdom during wartime. In the gathering darkness, Smith began sketching modifications that would either vindicate his radical thinking or end his career forever. If you enjoy dramatic, jaw-dropping stories, subscribe to World War II Archives Declassified. Let's grow this channel to 1,000 subscribers. The solution came to Smith at 3 in the morning, hunched over his desk in the cramped Rotol office, surrounded by oscilloscope readings and vibration analysis charts that had consumed the past 2 weeks of his life. The problem wasn't torque. It had never been torque. The contra-rotating propellers had eliminated the rotational forces perfectly. Quill's report confirmed that. But in solving one physics problem, Smith had inadvertently created another. The two propellers, spinning in opposite directions at slightly different speeds, were generating overlapping pressure waves in the airstream. At certain velocities, these waves synchronized into a destructive resonance that amplified rather than canceled, shaking the entire airframe with the force of a jackhammer. The mathematics were elegant in their brutality. At 370 SARMI, the forward propeller rotating at 1,825 RPM and the rear at 1,475 RPM created a beat frequency that matched the natural harmonic of the Spitfire's wing structure. The aircraft was essentially shaking itself apart. Smith's pencil moved rapidly across clean paper, recalculating gear ratios with the obsessive precision of a man who understood this was his final chance. The new configuration would run both propellers at closer speeds, 1,700 and 1,500 RPM respectively, shifting the critical beat frequency away from the airframe's resonant points. Additionally, he would modify the blade twist distribution, softening the aggressive angle changes near the tips that were generating the most violent vortices. When Chief Engineer Lithgow arrived at the office at dawn, he found Smith asleep at his desk. Surrounded by calculations that represented either salvation or the final miscalculation of a career built on unconventional thinking. "Malcolm," Smith said, jerking awake as Lithgow set down a cup of tea, "I know what went wrong." The modifications consumed 3 weeks of relentless work. Each propeller blade required hand finishing to tolerances measured in thousandths of an inch, work that tested the limits of British precision manufacturing. The gearbox was completely rebuilt with new ratios, each gear cut and polished until it meshed with mechanical perfection. Every component was balanced, tested, rebalanced, and tested again. Smith worked 18-hour days, personally inspecting every modification, rechecking every calculation. He had staked his professional reputation on this system twice already. There would be no third chance. The morning of March 18, 1944, brought clear skies and calm winds to Boscombe Down, conditions that seemed almost too perfect for what everyone understood would be the final test of Smith's controversial propeller system. Squadron Leader Quill approached the modified Spitfire with cautious optimism, tempered by vivid memories of his previous flight's violent conclusion. The propeller blades caught the morning light differently now, the revised geometry creating shadow patterns that seemed somehow more purposeful than the original configuration. The gearbox modifications tested perfectly during ground running, Lithgow reported, though his voice carried the tension of a man who understood that ground testing meant nothing until proven in actual flight. "We maintained stable operation through the entire power range without the harmonic vibrations that plagued the original system." Air Commodore Sorley had returned from London specifically to witness this second test, bringing with him a sense of institutional finality that infected everyone present. This flight would determine not only the fate of Smith's propeller system, but potentially the future direction of British fighter development. At precisely 10:15, Quill fired the Griffon engine and immediately noticed differences from the previous test. The sound was subtly different, still the complex harmonic created by contra-rotating propellers, but somehow more controlled, less aggressive in its mechanical resonance. Takeoff at 10:28 revealed the most dramatic improvement. Where the previous flight had required nearly full throttle to achieve acceptable climb performance, the modified aircraft now ascended at 2,000 feet per minute using only 80% power. The revised propeller geometry had eliminated much of the aerodynamic inefficiency that had plagued the original design. "Boscombe Control Test 27, climbing through 8,000 feet, Quill radioed, his voice carrying cautious excitement. "Climb performance is significantly improved. Handling characteristics remain excellent. Requesting clearance to test speed envelope. Test 27, you're cleared for speed testing. Exercise extreme caution approaching previous problem areas." Quill leveled the Spitfire at 10,000 feet and began his cautious exploration of the speed range that had nearly killed him 3 weeks earlier. At 300 mph, the aircraft flew with smooth precision. At 350 mph, still no unusual vibrations or handling anomalies. As the airspeed indicator crept past 370 mph, the speed at which the original system had become uncontrollable, Quill held his breath and waited for the violent shaking that had forced his emergency return. Instead, the Spitfire continued to accelerate smoothly. At 400 mph, the aircraft felt more stable than most fighters at half that speed. The elimination of torque reaction combined with the resolved vibration issues had created something unprecedented in aviation, a high-powered fighter that actually became more controllable as it approached its maximum performance envelope. Boscombe Control Test 27 has achieved 410 mph with no adverse handling characteristics, Quill reported, his voice now carrying genuine excitement rather than caution. The aircraft is completely stable and responsive. This is remarkable performance. From the control tower, Smith watched through binoculars as his modified Spitfire carved precise turns against the blue Hampshire sky. The contra-rotating propellers transforming the massive power of the Griffon engine into speed and agility that seemed to defy the laws of aviation physics. The sight vindicated not only months of technical work, but his fundamental belief that conventional approaches were insufficient for the challenges of modern warfare. Quill continued testing for another 25 minutes, exploring every aspect of the aircraft's performance envelope. High-speed dives revealed that the Spitfire could exceed 450 mph in controlled descent without developing the compressibility problems that affected many high-performance fighters. Tight turns at maximum power demonstrated handling that combined the agility of earlier Spitfire variants with the raw performance of the Griffon engine. At one point, Quill pushed the aircraft into a vertical climb at full throttle, a maneuver that would have been suicidal in the original Mark 21. The modified Spitfire clawed upward without a hint of instability, the contra-rotating propellers converting every ounce of the Griffon's fury into pure upward thrust. Landing at 11:32, Quill taxied to the hangar with the expression of a pilot who had just experienced something genuinely revolutionary. As he shut down the engine and climbed from the cockpit, his first words to the assembled engineers and officials carried the weight of professional expertise earned through years of combat flying. "Gentlemen," Quill announced, removing his flying helmet and looking directly at Smith, "what you have created is not simply an improved Spitfire. This is the finest fighter aircraft I have ever flown. The combination of speed, handling, and controllability exceeds anything in current service with any Air Force in the world." The small group stood in silence, absorbing the magnitude of what they had just witnessed. Air Commodore Sorley approached Smith with an expression that had transformed from skeptical authority to grudging admiration. "Mr. Smith," Sorley said formally, extending his hand, "I believe congratulations are in order. Your contra-rotating propeller system has exceeded our most optimistic performance predictions. The question now is how quickly we can begin production modifications for operational squadrons." Smith shook Sorley's hand, feeling the satisfaction of vindication tempered by awareness of the enormous challenges ahead. Proving that his system worked was only the beginning. Transforming experimental success into battlefield advantage would require manufacturing precision, pilot training, and logistical support on a scale that would test Britain's wartime industrial capacity to its limits. But for this moment, standing beside the aircraft that had transformed his radical idea into demonstrated reality, Smith allowed himself to imagine Spitfires with contra-rotating propellers dominating the skies over Europe, their impossible speed and agility providing the margin of superiority that could determine the outcome of the war itself. Quill walked over to where Smith stood, still staring at the modified propeller assembly. "You know what the most remarkable thing is?" The test pilot said quietly. "Above 400 miles, she doesn't just fly straight, she feels eager, like she's finally doing what she was meant to do all along." Smith nodded, understanding that Quill had articulated something profound about engineering and warfare. The Griffon engine had always possessed the power to make the Spitfire the fastest fighter in the sky. It had simply needed someone willing to think differently about how that power should be harnessed. The contra-rotating propellers spinning in opposite directions weren't fighting physics. They were working with it, channeling forces that others had tried to suppress into a symphony of mechanical perfection. As the spring afternoon lengthened across Boscombe Down, Smith stood beside his vindicated creation and allowed himself a moment of quiet satisfaction. The stupid idea had worked, and somewhere over the battlefields of Europe, that stupid idea might just save lives and win a war. The monster had been mastered. The Spitfire could finally fly. Don't just watch. Subscribe. Help World War II Archives Declassified. Hit 1,000 subscribers.